Every single galaxy in the observable universe is spinning too fast. Not by a small margin, not by a rounding error. They are spinning at velocities that should, by every known law of physics, cause them to fly apart. The stars at their outer edges should have long since scattered into the void, and yet they hold. Something invisible, something with mass, something that exerts gravity, is gripping them together. We have known about this invisible mass for over 90 years. We have mapped its distribution, modeled its behavior, and built our entire cosmological understanding of the universe around its existence. And yet, until very recently, not one piece of direct physical evidence had ever confirmed exactly what it is. When a physicist at the University of Tokyo published a paper that sent ripples through the astrophysics community, after methodically sifting through 15 years of archived data from one of the most sophisticated space telescopes ever launched, he found something, a signal, a specific, structured pattern of gamma rays, radiating from within our own galaxy, in a shape that perfectly traces the predicted outline of the Milky Way's invisible mass reservoir. And crucially, the energy of that radiation falls precisely within the range expected if two invisible particles had collided and annihilated each other. This is not a dramatic claim made by someone chasing headlines. This is a careful, methodical analysis of real observational data, pointing to the first potential direct observational signature of dark matter ever recorded. Whether it holds up to scrutiny will determine whether it reshapes modern physics. But even the possibility has physicists paying very close attention to understand why this matters so profoundly. You have to go back to 1933 to a Swiss astronomer with an unusual mind and an even more unusual personality. Working at the California Institute of Technology, Fritz Zwicky was born in 1898 in Varna, Bulgaria, to Swiss parents. He spent his formative years in Switzerland before eventually making his way to the United States, where he joined the faculty at Caltech and spent the better part of 5 decades there. Zwicky was by all accounts difficult to work with. He was blunt, combative, and sometimes openly contemptuous of colleagues he considered intellectually inferior, which, in his estimation, was most of them. He referred to his fellow astronomers as spherical bastards, meaning they were bastards no matter which angle you looked at them from. He was also, almost certainly, one of the most scientifically productive astronomers of the 20th century. Zwicky catalogued tens of thousands of galaxies. He pioneered the study of supernova, actually coining that very term to describe the catastrophic explosion of a dying star. He contributed foundational ideas to the study of neutron stars, cosmic rays, and gravitational lensing. His scientific output across his career ran to hundreds of papers on subjects as varied as crystal physics, jet propulsion, and the large-scale structure of the cosmos. And in 1933, almost as a footnote to a broader observational project, he noticed something that would generate 90 years of scientific confusion. Zwicky was measuring the redshift of galaxies in the Coma cluster. Redshift is the cosmic equivalent of the Doppler effect, the same principle that makes a passing ambulance's siren drop in pitch as it moves away from you. When a source of light is moving away from an observer, the light waves are stretched, shifting toward the red end of the spectrum. The greater the redshift, the faster the source is receding. By measuring the redshifts of individual galaxies, Zwicky could determine how fast they were moving relative to each other. Within the cluster, the Coma cluster is a collection of over 1,000 galaxies located roughly 320 million light-years from Earth and the constellation Coma beneath it. It is one of the densest known galaxy clusters in the nearby universe. When Zwicky measured the velocities of 8 galaxies within this cluster, he found something that refused to make sense. The galaxies were moving at speeds exceeding 2,000 kilometers per second relative to each other. Not 2,000 kilometers per hour, 2,000 kilometers per second. To put that in perspective, Earth orbits the Sun at roughly 30 kilometers per second. The galaxies in the Coma cluster were moving more than 60 times faster than that. For a gravitationally bound cluster of galaxies, a system held together by the mutual gravitational attraction of all its constituent mass, this should be impossible. When you know how fast objects are moving within a gravitational system, you can work backwards to calculate how much mass must be present to keep the system bound. If the objects are moving fast enough to escape, the system should have dispersed long ago. Zwicky ran the calculation. The visible mass of all the stars and gas in the Coma cluster, the mass that could actually be seen and measured, came up roughly 400 times too small to account for the velocities he was observing. Not missing by 10%. Not off by a factor of 2. 400 times too little mass. He concluded that there must be an enormous reservoir of mass hiding within the cluster mass that produced no detectable light. Mass that was invisible to every telescope then in existence. He called it dark matter. For decades, the idea was treated with polite skepticism. A single observation, no matter how carefully made, can always be explained away by measurement error, unknown systematics, or incomplete models. Zwicky was also not universally loved by the community, and this did not help the reception of his ideas. Dark matter sat on the margins of serious cosmological discussion for almost 4 decades. Then came Vera Rubin in the 1960s and 70s. Rubin, working with astronomer Kent Ford, began systematically measuring the rotational velocities of spiral galaxies. A spiral galaxy, like our own Milky Way, rotates around its central core. The stars at different distances from the center orbit at different speeds, and just as with the planets in our solar system, you can predict those speeds if you know where the mass is concentrated. In the solar system, most of the mass is in the Sun, so the planets further out orbit more slowly. Mercury zips around in 88 days, while Neptune takes over 160 years. This relationship, where rotational velocity decreases with distance from the mass center, is called a Keplerian profile, named after Johannes Kepler, who first described planetary motion. What Rubin found in galaxy after galaxy was that the rotation curves were flat. The stars in the outer regions of spiral galaxies were not slowing down as distance from the center increased. They were orbiting at roughly the same speed as stars much closer in, flat, not falling off. This was true not for one galaxy or 2 or 10, but for every spiral galaxy Rubin measured. Over 60 galaxies, the same pattern, over and over again. The only way to explain a flat rotation curve is to invoke enormous amounts of invisible mass distributed through and beyond the visible disk of the galaxy, in a roughly spherical structure called a halo. This extended dark mass keeps the orbital velocities high even at large radii, because the total enclosed mass keeps increasing as you move outward, unlike in the solar system, where almost all the mass is concentrated at the center. The dark matter halo is not concentrated where the stars are. It extends far beyond the luminous disk, enveloping the galaxy in an invisible gravitational sphere. Rubin's work was the turning point. It was systematic, rigorous, and reproducible. It could not be dismissed as an isolated anomaly. By the end of the 1970s, the scientific community had largely accepted that dark matter was real. The question was no longer whether it existed. The question became what it was. That question has proven extraordinarily difficult to answer. The term dark matter is really a placeholder, a name for something that exerts gravity. that cannot be made of the same particles as ordinary matter in sufficient quantities, and that does not interact with light in any detectable way. It does not emit light. It does not absorb light. It does not scatter light. It casts no shadow. Every tool astronomers normally use to study objects in the universe depends, fundamentally, on detecting electromagnetic radiation, light in its various forms, from radio waves to X-rays to gamma rays. Dark matter appears to be completely transparent to all of it. We know it exists because of what it does to things we can see. We infer its presence from its gravitational effects on stars, galaxies, and gas. We map its distribution by tracking how it bends light through a process called gravitational lensing. The warping of space-time around massive objects causes light from distant sources to curve around them, producing distorted and multiplied images that reveal the mass responsible even when no light comes from that mass itself. We can effectively weigh dark matter, trace its structure, and model its behavior in extraordinary detail. And we still have no confirmed idea what it actually is at the particle level. The cosmic microwave background, the faint afterglow of the Big Bang's heat, now cooled to just 2.7 degrees above absolute zero and suffusing the entire universe, gives us a precise accounting of the universe's total energy content. About 5% of the universe is ordinary matter, the stuff made of protons, neutrons, and electrons that forms everything you can see and touch and measure. About 27% is dark matter. The remaining 68% is dark energy, an even stranger component responsible for the accelerating expansion of the universe. This means that for every kilogram of ordinary matter, there are roughly 5.5 kilograms of dark matter. Everything humanity has ever studied, every atom, every molecule, every star, every planet, every human body represents less than 5% of what the universe is made of. Two theoretical candidates dominate the serious scientific discussion about dark matter's identity. The first are ixions, extremely low-mass particles originally proposed in the late 1970s as a solution to a puzzle in quantum chromodynamics. The theory of the strong nuclear force. Ixions are predicted to be so lightweight that enormous numbers of them would be required to account for the observed dark matter density. Experiments around the world are attempting to detect them by looking for the extremely rare conversions of ixions into photons in strong magnetic fields. No confirmed detection has been made. The second, and in many ways the more theoretically compelling candidate, is the weakly interacting massive particle, typically abbreviated as WIMP. The name is both descriptive and slightly ironic, given what WIMPs would imply for our understanding of the cosmos if they are confirmed to exist. WIMPs arise naturally from a theoretical framework called supersymmetry, which proposes that every particle in the standard model of particle physics has a corresponding supersymmetric partner particle with a much larger mass. The standard model is the most precisely tested theory in the history of science. It describes all known fundamental particles and 3 of the 4 fundamental forces, but it has known gaps. It does not explain gravity in quantum terms, and it does not account for dark matter. Supersymmetry is the most mathematically compelling extension of the standard model that has been developed, and it naturally predicts the existence of particles with exactly the properties we would expect from dark matter. WIMPs are predicted to have masses ranging from roughly 10 times the mass of a proton up to thousands of times the mass of a proton. They interact with ordinary matter only through gravity and the weak nuclear force, hence the name, weakly interacting. They do not interact via electromagnetism, which means they do not absorb, emit, or scatter light. They are not affected by the strong nuclear force which governs interactions inside atomic nuclei. They pass through ordinary matter almost as if it were not there. A WIMP could travel through the entire Earth from pole to pole with only an infinitesimally small probability of interacting with a single atom along the way. This makes them nearly impossible to detect. Underground laboratories, shielded from cosmic ray interference by hundreds of meters of rock, operate tanks of ultra-pure liquid xenon or silicon crystals at temperatures near absolute zero, hoping that the occasional WIMP will collide with a nucleus and produce a tiny recoil detectable above the thermal noise. The Large Hadron Collider at CERN has searched for evidence of WIMP production in high-energy particle collisions. Dozens of experiments across multiple decades have looked for WIMPs and found nothing definitive. But there is one other way WIMPs might make themselves known, and it follows from one of the most fundamental properties of particle physics. Every particle in the Standard Model has a corresponding antiparticle. The proton's antiparticle is the antiproton with the same mass but opposite charge. The electron's antiparticle is the positron. Again, identical mass, opposite charge. When a particle meets its antiparticle, both are annihilated in a burst of energy. The original mass is entirely converted to radiation, most commonly gamma rays, in an amount precisely described by Albert Einstein's equation relating energy to mass times the speed of light squared. The energy of those gamma rays is directly tied to the mass of the annihilating particles. Here is where WIMPs become theoretically detectable through astrophysics rather than particle physics experiments. In the Standard Model framework, the antiparticle of a WIMP is another WIMP. WIMPs are their own This means that whenever two WIMPs meet, they annihilate each other and release a characteristic burst of gamma radiation. The energy of that radiation corresponds to the mass of the WIMPs, somewhere in the range of 10 to thousands of times the mass of a proton, or equivalently, somewhere in the range of roughly 10 to several thousand giga-electron-volts in energy terms. If dark matter consists of WIMPs, and if WIMPs are densely enough distributed in certain regions of the galaxy, then WIMP annihilation events should be occurring continuously. The regions of highest dark matter density would produce the most annihilation events, and therefore, the strongest gamma-ray signal. By the modeling of dark matter's distribution around our galaxy, that region of highest density is the galactic center, and the extended spherical halo that surrounds the Milky Way's disk. The Fermi Large Area Telescope, launched by NASA in June 2008, is designed precisely to detect gamma rays from astrophysical sources. It surveys the entire sky every 3 hours in a broad energy range from about 20 million electron volts to over 300 giga-electron volts. Over 15 years of continuous operation, it has accumulated an extraordinary dataset, and buried within that dataset, according to Dr. Tomonori Totoni's November 2025 analysis, is something remarkable. Totoni's approach was painstaking rather than flashy. He began with the Fermi telescope's full archive of gamma-ray observations of the sky above and below the galactic plane, deliberately excluding the galactic plane itself, where the dense concentration of stars, gas, pulsars, supernova remnants, and the blinding radiation from the galactic center would overwhelm any subtler signal. He then systematically identified and removed every known astrophysical source of gamma rays from the dataset. Pulsars, the rapidly rotating neutron stars that beam gamma radiation with clockwork precision. Blazars, the jets of supermassive black holes pointing directly at Earth. Known supernova remnants. Catalogued binary star systems emitting gamma rays in their interaction zones. One by one, source by source, Totani stripped away the known contributions to the gamma-ray sky. What remained after this exhaustive subtraction was a diffuse gamma ray signal, not a point source from a single object, not a concentrated glow from a known region, a diffuse emission extending across the sky in a structured pattern. And the structure of that pattern, when plotted and compared against theoretical predictions, matched the predicted shape of the Milky Way's dark matter halo with striking precision. Dark matter is not distributed the same way as ordinary matter in our galaxy. Ordinary matter, the gas, dust, and stars, is concentrated primarily in the flat disk of the spiral galaxy along the galactic plane. Dark matter, according to decades of modeling based on galaxy rotation curves, gravitational lensing, and large-scale structure simulations, is distributed in a much more extended, roughly spherical halo surrounding the disk. The density of this halo peaks toward the galactic center and decreases gradually with distance, following a profile described mathematically by what astrophysicists call a Navarro-Frank-White profile, after the researchers who first derived it from computer simulations of structure formation in the early universe. The diffuse gamma-ray emission totani found in the Fermi residual data traced this profile. It was not a blob. It was not a disk. It was a spherical, halo-shaped distribution of gamma emission, centered on the Milky Way's center, with density falling off at the rates predicted by dark matter halo models. Then came the second piece of evidence. Totani examined the energy spectrum of the detected gamma rays. The energy distribution of the emission peaked at approximately 20 gigaelectron volts. 20 gigaelectron volts is a remarkable number because it falls squarely within the energy range predicted for gamma rays produced by the annihilation of WIMPs with masses in the range of 40 to 80 gigaelectron volts divided by the speed of light squared, a mass range that has been theoretically well motivated for decades, and that falls within the accessible range of supersymmetric models. Two independent lines of evidence, then, both pointing in the same direction. The spatial distribution of the excess gamma emission matches the predicted dark matter halo shape, and the energy spectrum of that emission matches the predicted signature of WIMP annihilation. This is not a case of one suggestive observation being overinterpreted. It is a case of two distinct observational properties, independently predicted and independently measured, aligning with theory. To appreciate what this finding means in context, it is worth understanding how long this search has been going on, and how little direct evidence has been found. Since Zwicky's 1933 observation of the Coma cluster, and since Rubin's comprehensive galaxy rotation surveys in the 1970s, evidence for dark matter's existence has continued to accumulate from multiple independent directions. The collision of galaxy clusters, particularly the famous Bullet cluster observed in 2006, provided what many physicists consider the most compelling evidence that dark matter is real and that it cannot simply be explained by modifying our understanding of gravity. When two galaxy clusters collide, the hot gas, which makes up most of the visible matter, is slowed and heated by electromagnetic interactions. But the dark matter, if it is as weakly interacting as theorized, passes through the collision unimpeded. The Bullet cluster observation captured two clusters shortly after collision, and X-ray observations revealed that the hot gas had been displaced from the gravitational mass, CENTRES, as revealed by gravitational lensing. The mass was somewhere, the gas was not. The only explanation consistent with the data was that most of the mass, invisible to X-ray, had continued moving while the ordinary matter piled up. Computer simulations of cosmic structure formation, using observed parameters from the cosmic microwave background, successfully reproduce the large-scale structure of the universe, the web-like network of galaxy filaments, clusters, and voids that characterizes the observed cosmos only when dark matter is included in the model. Without dark matter, the simulations produce a universe that looks nothing like the one we observe. With dark matter, and specifically with cold dark matter, meaning dark matter particles that were moving slowly at the time of matter equality in the early universe, the simulations reproduce the observed structure with remarkable accuracy. All of this evidence is gravitational or structural. It tells us that dark matter exists, approximately how much of it there is, and roughly how it is distributed. None of it tells us what dark matter particles are at the fundamental level. None of it gives us a direct detection of the particle itself. Totani's finding, if confirmed, would be the first, and the astrophysics community is accordingly both excited and cautious. The caution is, well, there is history here, and the history is instructive. In 2009, scientists working with the Pamela satellite reported an excess of positrons in cosmic rays, antiparticles of electrons, at energies consistent with what might be expected from dark matter annihilation. The excess was real. The question was what had produced it. The initial interpretation leaned toward dark matter. Over the following years, pulsars emerged as a more likely explanation. The signal from dark matter and the signal from dense populations of spinning neutron stars in our galaxy were difficult to That particular story ended not in a dark matter discovery, but in a lesson about how difficult it is to attribute an astrophysical signal to dark matter specifically, rather than to some conventional but initially overlooked source. In 2014, an excess of gamma rays from the direction of the galactic center, often called the galactic center excess, attracted enormous attention. The excess was concentrated at energies of 1 to 3 gigaelectron-volts, consistent with the annihilation of dark matter particles with masses in the tens of gigaelectron-volts range. Papers were published arguing it was the clearest signal yet of dark matter. Then began the alternative explanations: unresolved millisecond pulsars, cosmic ray interactions with the dense interstellar gas near the galactic center, emission from stellar remnants. The debate continues to this day, without definitive resolution in either direction. Totani was aware of this history. His analysis differs from the galactic center excess work in a critical way. He explicitly excluded the galactic center and the galactic plane from his analysis, focusing instead on the high-latitude diffuse emission where contamination from conventional gamma-ray sources is far lower. This is a deliberate methodological choice designed to address the central criticism that has haunted every previous dark matter signal claim that the signal region is too crowded with known sources to cleanly isolate a dark matter contribution. But removing the galactic plane also removes the region of highest predicted dark matter density, which means the signal, if it is from dark matter, is detecting the halo rather than the central cusp. This has implications for the inferred density of dark matter and the required annihilation rate, and here lies one of the more challenging aspects of the finding: for the observed gamma-ray signal to be produced by WIMP annihilation, the density of WIMPs in the halo would need to be higher than standard models predict. The standard cold dark matter models, calibrated against large-scale structure observations and the cosmic microwave background, give specific predictions for the density profile of dark matter halos. The signal Totani observes requires an annihilation rate that, when worked backwards, implies either a higher than expected local density of WIMPs or a WIMP annihilation cross-section, the effective probability of two WIMPs interacting when they pass near each other that is larger than some theoretical estimates prefer. This is not necessarily a fatal objection. Dark matter density predictions have uncertainties of their own, particularly in the inner regions of halos, where baryonic feedback from star formation and supernova explosions can redistribute matter and potentially concentrate or reduce dark matter density. The physics of galaxy formation is messy in ways that are difficult to fully capture in simulations, but it means the finding requires more work before it can be conclusively attributed to WIMP annihilation rather than an overestimate of the true halo density. There is also the question of alternative astrophysical explanations. Even in the high-latitude sky, far from the galactic plane, there are sources of gamma rays that could potentially mimic a diffuse dark matter signal. Unresolved point sources, blazars, radio galaxies, and other extragalactic objects, too faint to be individually catalogued, contribute to the diffuse gamma ray background. The exact contribution of these sources at high latitudes is subject to ongoing modeling. If the source subtraction process Totani applied to the Fermi data was incomplete, or if there are unaccounted for source populations contributing at the energy range of the signal, the residual could be partially or wholly explained without invoking dark matter. Totani acknowledges these uncertainties. The paper is not framed as a definitive detection, but as a significant signal warranting serious investigation. The physics community's response has been to treat it accordingly, neither dismissing it nor declaring victory, but directing increased attention and follow-up analysis toward understanding it better. Professor Carlos Franke, a cosmologist at Durham University, who is one of the architects of the cold dark matter framework that underlies modern cosmology, has weighed in on the significance of the search. Frank has compared finding the true nature of dark matter in terms of its importance to human understanding to Charles Darwin's theory of evolution by natural selection. Darwin's work overturned a fundamental assumption about the origins of life. Finding dark matter's particle identity would overturn a fundamental assumption about what the universe is made of. Frank's point is that such discoveries are not made lightly. You do not claim to have found the particle identity of dark matter unless the evidence is unambiguous. And the evidence, as of now, is compelling but not yet unambiguous. What would make it unambiguous? Consistency. If the gamma-ray signal is truly from WIMP annihilation in the Milky Way's dark matter halo, then the same signal should appear from other systems with dark matter halos. The dwarf spheroidal galaxies orbiting the Milky Way are particularly useful targets. These small, ancient galaxies, with names like Draco, Sculptor, Ursa Minor, and Fernax, are estimated to contain extremely high ratios of dark matter to ordinary matter, making them among the best places in the local universe to look for dark matter annihilation signals. If the WIMPs responsible for the Milky Way halo signal exist in the same density and with the same annihilation rate, they should also be producing detectable gamma ray emission from these satellites. Current upper limits from analysis of dwarf spheroidal galaxies with the Fermi telescope have so far not detected significant excess gamma-ray emission. This is sometimes cited as tension with WIMP models, but the sensitivity of those analyses depends critically on the assumed dark matter profiles of the dwarfs, which are poorly constrained. More data, better modeling, and improved analysis techniques will sharpen those constraints. This is where new observatories enter the picture. The Vera C. Rubin Observatory, located at Cerro Pachín in northern Chile at an altitude of roughly 2,600 meters, began scientific operations in June 2025. It houses the largest digital camera ever built for astronomical use, a 3,200,000,000 pixel array attached to an 8.4-meter primary mirror. Every 15 seconds, the camera captures an image covering 9.6 square degrees of sky, roughly the apparent area of 45 full moons laid side by side. The telescope cycles through the entire accessible southern sky every few nights, accumulating a dataset of staggering scale. Over its planned 10-year legacy survey of space and time, the Rubin Observatory will collect more than 60 petabytes of raw imaging data, 60 million gigabytes, produced by imaging the sky hundreds of thousands of times across multiple filters. The telescope will catalog billions of galaxies and map the positions and shapes of objects down to extremely faint magnitudes. Among its primary science goals is the measurement of weak gravitational lensing across enormous swaths of sky, which will allow the three-dimensional dark matter distribution of the cosmos to be mapped with far greater precision than has previously been possible. Critically, for the WIMP question, the Rubin Observatory will also enormously expand the known population of ultra-faint dwarf galaxies orbiting the Milky Way. These systems are so faint that most of them remain undiscovered. Their stellar populations are sparse, their total luminosities are tiny, and they can only be detected through statistical analysis of stellar density enhancements against the background sky. Rubin's sensitivity will reveal dozens, potentially hundreds, of new satellite galaxies, each a new target for dark matter annihilation searches with gamma-ray telescopes. More systems mean better statistics. Better statistics mean more constraining upper limits, or, if the signal is there, more chances to detect it. The first data releases from Rubin are expected in 2026, and the astrophysics community is anticipating them with considerable impatience. Meanwhile, particle physics continues its own parallel search. The Large Hadron Collider at CERN has been running since 2008, and while no supersymmetric particles have been discovered in Run 1 or Run 2, the current Run 3 operations are extending sensitivity into new parameter space. The absence of supersymmetric particles at the energies explored so far does not rule out WIMP's supersymmetry has many variants, and the parameter space is vast, but it has progressively narrowed the range of viable models. Direct detection experiments continue to improve. The LUX-Zeppelin detector, located 1.5 kilometers underground in the Sanford Underground Research Facility in the Black Hills of South Dakota, currently represents the most sensitive dark matter direct detection experiment in the world. It uses 10 tons of liquid xenon at cryogenic temperatures, monitored by arrays of photomultiplier tubes capable of detecting the faint flashes of light produced when a WIMP occasionally scatters off a xenon nucleus. LUX-Zeppelin completed its first major science run and published results in 2022, finding no signal consistent with WIMPs across a broad mass range. But it is continuing to run, accumulating exposure time, and the next generation of liquid xenon experiments, including the proposed Inton-scale detectors, would push sensitivity another order of magnitude deeper. The relationship between the direct detection limits and the gamma ray signal is important. If Titani's signal is from WIMP annihilation, the required annihilation cross-section and mass together imply a specific prediction for what direct detection experiments should see. If the LUX-Zeppelin detector, with its current and projected sensitivity, continues to see nothing while the gamma-ray signal persists and strengthens, that tension will need to be resolved. Either the WIMPs have unusual properties that suppress direct detection while allowing annihilation, which is theoretically possible in certain models, or the gamma-ray signal has a different origin. It is worth stepping back to appreciate the broader scientific context within which this search is being conducted. Dark matter is not just a cosmological curiosity. It is structurally fundamental to the universe we observe. In the earliest moments after the Big Bang, the universe was a hot, dense plasma of ordinary matter, radiation, and dark matter. Ordinary matter and radiation were tightly coupled, bouncing photons back and forth in a way that prevented matter from collapsing under its own gravity. Dark matter, being invisible to radiation, was not coupled to it. It could begin collapsing under gravity while ordinary matter remained in the plasma state. This meant that dark matter collapsed first, forming the gravitational scaffolding, the wells and filaments of the cosmic web into which ordinary matter later fell. The first stars formed inside concentrations of dark matter. The first galaxies assembled along dark matter filaments. The large-scale structure of the universe, the cosmic web of galaxy clusters and filaments, and the vast empty voids between them, reflects the underlying distribution of dark matter more directly than it reflects the distribution of ordinary matter. Without dark matter, the universe would not contain galaxies. The gravitational fluctuations in the ordinary matter alone, as we observe them in the cosmic microwave background, are too small and too slow to have collapsed into the structures we see today within the time the universe has existed. Dark matter provides the necessary extra gravitational pull to accelerate that collapse. You cannot build a universe that looks like ours without it. This is also why the identification of dark matter's particle nature is considered one of the most important open questions in all of science. It is not merely about filling a gap in a table of particle properties. Understanding what dark matter is will illuminate the conditions of the earliest universe, the particle physics beyond the standard model, and potentially the ultimate fate of the cosmos. The Fermi telescope's contribution to this story spans the entire history of the search for WIMP annihilation signals. Since its launch in 2008, the Large Area Telescope aboard Fermi has surveyed the gamma-ray sky with unprecedented sensitivity and coverage. It has detected thousands of point sources, mapped the diffuse emission from the Milky Way's interstellar medium in detail, observed gamma-ray bursts at cosmological distances, and built the most comprehensive all-sky gamma-ray catalog ever assembled. It was designed with the WIMP signal in mind. Its energy range was chosen specifically to overlap with the predicted WIMP annihilation spectrum for 16 years. Careful analysis of Fermi data found tantalizing hints, but nothing definitive. The galactic center excess generated enormous interest, but remained contested. The collaboration between observers and theorists produced progressively more refined upper limits on WIMP properties, systematically ruling out large swaths of parameter space, but never pinning down a signal. Totoni's approach of going back to the archive with a new analysis strategy, stripping out not just the galactic plane, but every individually resolvable source, and examining the residual, high-latitude diffuse emission, represents the kind of methodological innovation that drives progress. In a field where the data exists, but the signal may be buried in complexity, the result is a signal at a level of statistical significance that demands attention. Totani reports the detection at a level above 5 sigma, 5 standard deviations, above the background in the morphological match between the observed emission and the predicted dark matter halo. 5 sigma is the conventional threshold in particle physics for claiming a discovery. In astrophysics, where systematic uncertainties are harder to control, the bar is sometimes considered higher. The community is debating whether the analysis fully accounts for all possible systematic effects, and independent groups are working to reproduce and extend it. The path from a compelling signal to an accepted discovery in astrophysics is not short. The process requires independent confirmation, exploration of alternative explanations, refinement of the analysis, and ultimately a body of evidence from multiple instruments and approaches that collectively leaves no reasonable doubt. We are at the beginning of that process, not the end, but the beginning of that process. when it involves a 15-year Fermi archive and a carefully controlled analysis. Producing a spatially coherent signal at the right energy is itself significant. It is more than was available yesterday, and in a field where the last genuinely compelling new lead, the galactic center excess, emerged over a decade ago. A new, methodologically distinct signal from a different part of the sky, produced by a different analysis strategy and pointing to the same class of dark matter candidate, is exactly the kind of development that energizes an entire field. The question of what dark matter is has a certain philosophical weight to it that goes beyond its practical importance to cosmology. We are made of the minority component of the universe's mass. Everything we know, everything we have built, everything we have ever studied, represents the thin, luminous frosting on a much larger invisible cake. The atoms in your body, the air you breathe, the ground beneath your feet, all of it is ordinary matter. The stuff that interacts with light, that forms chemical bonds, that can be seen and touched and measured, and all of it adds up to less than 5% of what the universe contains. The rest, the dark matter and dark energy, exists around us and through us, shaping the large-scale architecture of the cosmos, influencing the motion of every galaxy, and yet leaving no trace in any ordinary experiment. A dark matter particle is passing through your body right now, and your body is almost completely transparent to it. If WIMPs exist at the density required to explain the observed dark matter, roughly 100 million of them are streaming through every square meter of Earth's surface every second. None of them stop. None of them slow down. None of them leave any detectable mark. And yet, collectively, they constitute most of the mass of the galaxy. There is something intellectually vertiginous about that. The matter you are made of is exceptional, not typical. It is the strange, photon-interacting, chemistry-capable minority fraction. The cosmos is mostly something else entirely, something that has been governing the motion of galaxies for over 13 billion years, and has so far refused to identify itself. Vera Rubin, whose observatory now bears her name, put it well near the end of her life. She spent decades documenting dark matter's gravitational influence and said, she found it remarkable that the universe had managed to keep such a fundamental secret for so long. The flat rotation curves she measured are so consistent, so universal across spiral galaxies of all sizes and ages, that the presence of dark matter halos cannot seriously be doubted. What remains is the detail, the nature of the particle itself. The current moment in that search is genuinely exciting, for several reasons converging at once. Totoni's November 2025 analysis provides a new observational constraint from an unexpected direction, the highly diffuse gamma-ray sky that aligns with WIMP predictions in both spatial and spectral character. The Vera Rubin Observatory is beginning its survey, and its first data releases will expand the inventory of dark matter targets in the local universe by a substantial factor. The Lux-Zeppelin experiment is continuing to accumulate exposure, testing the direct detection parameter space that overlaps with the gamma-ray signal's implications. And at the Large Hadron Collider, ongoing Run 3 data collection is extending the mass reach for supersymmetric particles. These are not independent searches operating in isolation. They are complementary probes of the same underlying physics. A WIMP discovery through gamma-ray observations would make specific predictions for direct detection rates. A direct detection would predict specific production rates at particle colliders. A collider production would predict specific cosmological consequences, traceable through large-scale structure surveys. The searches are triangulating on the same target from multiple directions. This convergence is deliberate. The theoretical WIMP candidate was always compelling precisely because it makes specific predictions that can be tested by multiple methods. The frustration of 30 years of null results in direct detection experiments had begun to erode enthusiasm for WIMPs as a candidate. But null results in direct detection, while constraining, do not rule out WIMPs. Generally, they rule out specific WIMP models with specific cross-sections. Other models remain viable, and the gamma-ray detection, if confirmed, would not be in contradiction with the direct detection upper limits. At the level of current sensitivity, what comes next will determine whether November 2025 represents a footnote or a watershed. The Fermi telescope is still operating, though it has been in space for over 16 years now. Future gamma-ray observatories, including the proposed Compton spectrometer and imager, and the next-generation Cherenkov telescope array in Chile, which combines over 100 individual telescopes into a single integrated observatory with sensitivity exceeding Fermi's by an order of magnitude at the high end of the energy spectrum, will bring new capabilities to bear on the problem. The Cherenkov telescope array is designed specifically with dark matter searches as one of its primary science cases, and its sensitivity to the high energy end of the WIMP mass range is substantially better than any existing instrument. The story of dark matter is 90 years old and still unresolved. That is an unusual duration for a mystery at the center of the scientific enterprise. Most fundamental questions in physics and astronomy are resolved within decades of their first clear formulation. Dark matter has proven genuinely elusive, not because scientists have not been looking, but because whatever dark matter is, it interacts with the tools of science so weakly as to be almost perfectly hidden. Almost, the word almost carries enormous weight. Gravity cannot be hidden. Any mass, no matter how electromagnetically dark, will curve space-time and pull other objects toward it. Dark matter has been detected gravitationally for 90 years. And in that time, the case for its existence has only strengthened. Every new telescope, every new galaxy survey, every new gravitational lensing analysis, every new simulation of cosmic structure has confirmed and refined the picture. The question is not whether dark matter exists. The question is whether we have now, for the first time, detected a direct product of its particle nature, a gamma ray produced in the annihilation of two dark matter particles colliding somewhere in the vast, cold darkness of the Milky Way's halo. The answer is not yet certain, but the signal is there, shaped like a halo, peaked at the right energy, emerging from a cleaned dataset after 16 years of careful observation. It is the most specific thing we have ever seen that looks like dark matter announcing itself, and the community of scientists following this signal, in underground labs in South Dakota and Britain, in telescopes on Chilean mountainsides, in particle accelerators beneath the Franco-Swiss border, and in the growing archive of the Fermi telescope, are not resting. They are triangulating, comparing, testing, and refining, because if the signal is real, confirming it would be one of the most consequential discoveries in the history of natural science. It would not merely solve a 90-year-old mystery in cosmology. It would open a window into the particle physics of the early universe that has been sealed since the first second after the Big Bang. Every generation of scientists has inherited an expanding frontier of the unknown and has pushed it further back. The people doing cosmology today are working at the boundary where the known meets the unknowable, equipped with instruments and methods that would have been unimaginable to Fritz Zwicky when he sat at his desk at Caltech and worked out that the Coma cluster should not exist. He did not know what dark matter was. He only knew that something invisible had to be there. 90 years later, something visible, faint but structured, energetic and shaped, may be telling us what that something finally is. If you found this exploration of one of science's most enduring mysteries as compelling as we do, consider sharing it with someone who would appreciate it, and subscribing so you don't miss what comes next. Because in cosmology right now, what comes next is genuinely unpredictable. And that is precisely what makes it worth watching. To understand the full depth of what Totani's finding represents, it helps to think about what the Fermi telescope actually sees and how it builds a picture of the gamma ray sky. Gamma rays are the highest energy form of electromagnetic radiation. They sit at the extreme end of the spectrum, far beyond visible light, beyond ultraviolet, beyond X-rays. A single gamma-ray photon at 20 gigaelectron volts carries billions of times more energy than a photon of visible light. They are produced by the most violent processes in the universe: nuclear reactions, particle annihilation, the acceleration of charged particles to near-light speeds in the crushing magnetic fields around neutron stars and black holes. They are also impossible to observe from the ground. Earth's atmosphere absorbs gamma rays completely, which is why you are not bombarded with them every time a cosmic event occurs. This is fortunate for biological life on Earth, but unfortunate for astronomers. To observe gamma rays, you need to be in space. The Fermi Large Area Telescope achieves this by using a different detection strategy than ordinary optical telescopes. When a gamma ray enters the detector, it converts into an electron-positron pair. Upon interaction with the detector material, this is pair production, one of the fundamental processes of quantum electrodynamics. The paths of the electron and positron are tracked through layers of silicon strip detectors, and their trajectories allow the original direction of the gamma ray to be reconstructed. A calorimeter at the base of the instrument measures the total energy deposited, giving the gamma rays energy. By reconstructing both direction and energy for millions of individual photon events, the Fermi telescope builds up a map of the gamma ray sky in both angular position and spectral distribution. The result, accumulated over 16 years, is an extraordinary dataset. Over 1 billion gamma ray photons above 100 million electron volts have been detected and catalogued. Thousands of individual sources have been identified and characterized. The diffuse background from the Milky Way's interstellar medium, produced primarily by cosmic ray protons colliding with gas and producing pions that decay into gamma rays, has been mapped in detail. The extragalactic background, the sum of unresolved sources from across the observable universe, has been measured and partially decomposed. Against this complex, multi-component sky, Totani was searching for something that should, in principle, have a predictable and distinctive signature. Not a point source, not a known class of extended emission, a faint, diffuse glow in a specific shape, the dark matter halo at a specific energy around 20 gigaelectron volts. The challenge is that detecting such a signal requires not just sensitivity to low-level diffuse emission, but the ability to distinguish it from the superposition of all other diffuse gamma-ray contributions at the same energies. This is fundamentally a problem of foreground subtraction, the same challenge faced by cosmologists trying to extract the cosmic microwave background signal from the bright emission of our own galaxy, or by astronomers trying to detect faint, distant galaxies behind the glare of nearby stars. Totani's methodology for this subtraction was built on the Fermi collaboration's own source catalogues, which have been refined through multiple data releases over the years. The fourth Fermi lot source catalogue, known as 4FGL, lists over 5,000 point sources. Totani masked these known sources and then modeled the contributions from the major diffuse emission components: the galactic interstellar emission, the isotropic extragalactic background using spectral and spatial templates derived from multi-wavelength data, After this model-based subtraction, the residual represents emission that cannot be accounted for by known sources and known diffuse components. The residual, Totani finds, is not uniform across the sky. It is structured. It is brighter toward the galactic poles and falls off in a pattern, consistent with a spherical halo profile rather than with disconcentrated emission. This morphological distinction is precisely what distinguishes a dark matter halo signal from a missed contribution of ordinary astrophysical sources, which would be concentrated toward the galactic plane. The energy spectrum of the residual is the second key characteristic. If this emission were from a population of unresolved ordinary astrophysical sources, blazars for example, which are the most numerous type of source at high galactic latitudes, the spectral shape would follow a characteristic power law distribution, meaning emission would fall steadily as energy increases. Instead, the residual shows a peak at approximately 20 GeV before turning over, which is exactly the spectral shape predicted for WIMP annihilation. A thermal WIMP, the type most naturally produced from the Big Bang in sufficient quantities to account for the observed dark matter density, annihilates with a cross-section that produces a characteristic spectral peak at half the WIMP mass. The observed peak energy of 20 GeV therefore implies a WIMP mass of approximately 40 GeV. 40 GeV is a specific and theoretically interesting mass. It is within the reach of the Large Hadron Collider's collision energies. It is within the sensitive range of ton-scale liquid xenon direct detection experiments. It falls in the part of supersymmetric parameter space that has been theoretically well motivated for decades, and it corresponds to a particle that would have been produced in the correct abundance during the Big Bang through the mechanism called thermal freeze-out to account for the observed dark matter density without requiring any special fine-dash tuning. This last point deserves elaboration. In the early universe, at temperatures above roughly 1 trillion degrees, WIMPs would have been created and destroyed in equilibrium with the hot plasma of ordinary particles. As the universe cooled, the rate of WIMP annihilation fell. Eventually, the temperature dropped low enough that WIMPs could no longer be created from the available thermal energy, but they were also by then rare enough that annihilation events were infrequent. The WIMPs that existed at that moment, called the freeze-out epoch, became the surviving relic population. The density of WIMPs today is the relic density from this freeze-out. For a particle with the weak force interaction strength, the relic density from thermal freeze-out comes out very close to the observed dark matter density. This remarkable coincidence that a particle motivated entirely by particle physics considerations, interacting with the weak force strength, naturally produces approximately the right amount of dark matter, is sometimes called the WIMP miracle. It is one of the strongest theoretical reasons why WIMPs have been considered the leading dark matter candidate for 3 decades. The WIMP miracle has never been a proof. It has been a suggestive coincidence that motivates the search, and the search, despite enormous experimental effort, has not yet found a WIMP. Each new generation of experiments has pushed the sensitivity deeper, ruling out more of the theoretically expected parameter space, and each null result has increased the tension between theory and observation. Totani's finding does not resolve this tension. If anything, it adds complexity. A gamma-ray signal of the observed strength requires an annihilation rate that, for thermal relic WIMPs with the natural freeze-out cross-section, implies a local dark matter density somewhat higher than the standard halo models suggest. This is either evidence that the halo models need refinement, or it suggests that that the WIMP abundance in the relevant part of the halo has been enhanced by some mechanism, or it could indicate that the annihilation cross-section is velocity in a way that enhances it in the slow-moving cold dark matter environment of the galactic halo compared to the early universe freeze-out epoch. Each of these possibilities is theoretically realized in specific dark matter models. Sommerfeld enhancement, for instance, is a quantum mechanical effect that increases the annihilation cross-section when two dark matter particles approach each other slowly. Exactly the conditions in a cold dark matter halo. Models incorporating Sommerfeld enhancement naturally predict a higher annihilation rate today compared to freeze-out, which could reconcile the signal strength with the direct detection, non-observations. The theoretical particle physics community is actively working through these implications. The observational signal, if confirmed, is a data point that constrains models rather than simply providing an open-ended endorsement of WIMPs. Not all WIMP models are consistent with it. Models that produce the right spectral shape and the right annihilation rate are a specific subset. Identifying which models survive all constraints from the gamma-ray signal, from the Fermi diffuse background measurements, from the direct detection upper limits, from the cosmic microwave background. Relic density is a project that will occupy theorists for years. This is how particle astrophysics progresses. A signal motivates theoretical scrutiny. Theoretical scrutiny identifies predictions. Predictions drive new observations. New observations refine or challenge the theoretical models. The loop iterates until either the signal is confirmed as a discovery or it is explained away by some combination of conventional physics and better astrophysical modeling. The Milky Way's dark matter halo is not the only target relevant to this process. The local group of galaxies, the roughly 60 gravitationally bound galaxies in the Milky Way's immediate neighborhood, including the Andromeda Galaxy, the Magellanic Clouds, and dozens of smaller satellites, all contain dark matter halos. The Andromeda Galaxy, or Messier 31, is the nearest large spiral galaxy, sitting roughly 2.5 million light-years away. Its dark matter halo, like the Milky Way's, should be producing a diffuse gamma-ray signal. If WIMPs are responsible for the Milky Way signal, the angular extent of Andromeda on the sky is large, enough that future telescopes with better angular resolution than Fermi could potentially resolve the halo profile and compare it to the theoretical prediction, the Magellanic Clouds, the two irregular galaxies that orbit the Milky Way, at distances of about 160,000 and 200,000 light-years, respectively, are also embedded in dark matter halos. The large Magellanic Cloud in particular, with its bright stellar population and proximity, has been extensively studied across wavelengths. Its dark matter halo overlaps substantially with the outer edge of the Milky Way's own halo, creating a complex environment for signal analysis, but also offering an independent test of the WIMP interpretation beyond the local group. Galaxy clusters like the Coma cluster, the very system Zwicky observed in 1933, are massive enough that their dark matter content should produce detectable gamma-ray emission if the annihilation rate inferred from Totoni's analysis is correct. The Fermi telescope has searched for gamma-ray emission from clusters and found no significant excess, but the distance to even the nearest clusters means the signal would be fainter, and the analysis of cluster emission is complicated by the strong gamma-ray emission from the active galaxies concentrated in clusters. Better sensitivity from future telescopes could make cluster searches significantly more constraining. The search for dark matter has a sociological dimension as well as a scientific one. It has consumed enormous resources, billions of dollars in telescope and detector construction, decades of researcher time, hundreds of thousands of person-hours of data analysis. The Large Hadron Collider's construction cost roughly $10 billion. The underground liquid xenon experiments cost hundreds of millions of dollars each. Space telescopes like Fermi cost over $700 million. These are public investments in fundamental science with no guaranteed return, made on the basis that understanding what the universe is made of is worth pursuing even without a guaranteed practical application. The absence of a definitive dark matter detection through any of these methods has periodically prompted soul-searching in the community. Some physicists have argued that the null results from direct detection experiments accumulated across multiple generations of experiments that have improved sensitivity by many orders of magnitude suggests that WIMPs may not exist in the theoretically expected parameter space. They argue that alternative dark matter models, ixions, sterile neutrinos, primordial black holes, or models with more exotic properties deserve more attention and resources. These arguments are legitimate. Science should follow the evidence, and the evidence for thermal relic WIMPs from direct detection has been uniformly negative. But the gamma-ray sky is a different probe with different sensitivities, and a signal in the gamma-ray channel that is absent in direct detection is theoretically possible in models where the annihilation and scattering cross-sections are not simply related. The broader point is that dark matter research is not a single experiment that has failed. It is a collection of complementary searches, each probing different aspects of a problem that is genuinely hard. The difficulty reflects the nature of the target particles that interact so weakly that they have evaded detection by the most sensitive instruments ever built. The fact that we can detect their gravitational presence at all, across scales from the Coma cluster to individual dwarf spheroidal galaxies, to the rotation curves of spiral galaxies, to the pattern of the cosmic microwave background, is itself a scientific achievement. The problem is not that dark matter is hiding, it is that we lack the right key for the lock. Every new observation, every new analysis, every new instrument brings the possibility that the right key will be found. Totani's analysis of the Fermi archive may be one such key, or it may prove to be a key that does not quite fit. The next few years of observations and analysis will determine which dot. What is clear is that the dark matter problem is not going away. The evidence for its existence continues to accumulate. The observational infrastructure for detecting its particle signature is growing more powerful, and the motivation for solving it. Understanding the nature of 80% of the universe's matter content remains as fundamental as any questions science has ever asked. There is a strange intimacy to this search when you consider it from a personal perspective. You are made of ordinary matter, protons, neutrons, electrons, photons, the full panoply of the standard model. But you move through space that is permeated by dark matter at densities. We can calculate precisely enough to say that, right now, a stream of dark matter particles is passing through every cubic centimeter of space you inhabit. These particles, whatever they are, interact so rarely with the matter of your body that the probability of even one interaction occurring in your lifetime is essentially zero. You will never directly feel dark matter. You will never see it, taste it, or measure it with any sense you possess. And yet it shaped the galaxy you were born in, made possible the formation of the solar system you inhabit, and will govern the eventual fate of the galaxy long after the sun has exhausted its fuel. That is the strange reality of a universe in which most of the matter is invisible. The world we experience, the world of atoms and light and chemistry and gravity, on human scales, is a thin, luminous layer wrapped around a much more massive, invisible scaffolding. The scaffolding was there before the atoms. It will be there after the atoms have been recycled through generations of stars. It is, in a certain sense, more fundamental to the structure of the cosmos than the matter we are made of. Understanding what that scaffolding is made of, whether it is WIMPs at 40 gigaelectron volts, axions at fractions of a microelectron volt, something entirely different, or some combination of components, is not merely an intellectual exercise. It is a confrontation with the fundamental architecture of reality. And the signal in the Fermi data, shaped like a halo and peaked at 20 gigaelectron volts, may be the first time that architecture has spoken clearly enough for us to hear it. The cold case opened by Zwicky in 1933 is not yet closed, but it is, perhaps, closer to resolution than it has ever been. The evidence is accumulating. The instruments are improving. The analysis techniques are being refined. And somewhere in the data already collected, or in the data being collected right now by telescopes in space and on Chilean mountaintops and in underground laboratories, the answer may already exist, waiting to be uncovered. Science, at this level of the frontier, is not a linear march toward discovery. It is a long, patient, often frustrating process of building and testing, of following false leads and eliminating them, of improving sensitivity and precision until the signal emerges above the noise. The people doing this work know that any given observation may not yield a definitive answer. They do it anyway, because the question demands to be answered, and because someone has to be the one looking. The next generation of instruments is already being built. The Cherenkov telescope array in Chile and in the Canary Islands will listen to the high-energy gamma-ray sky with sensitivity that dwarfs anything yet available. The next generation of direct detection experiments is being planned. The Rubin Observatory is beginning to map the local universe in unprecedented depth. The Large Hadron Collider is continuing to explore the high-energy particle frontier. And physicists around the world are studying Totoni's paper, checking the analysis, trying to reproduce it, and working out what it would mean if it is right. Dark matter is still there. It has always been there. Now, for the first time, we may be hearing it. To fully appreciate why the Totani signal is being taken seriously by physicists who have lived through many false alarms, it helps to understand what has changed in the quality and quantity of the Fermi dataset over the 16 years since the telescope's launch. This is not a new instrument looking at the sky for the first time. It is a mature observatory whose dataset has grown more powerful with each passing year, simply through the accumulation of observing time. Gamma-ray astronomy, unlike optical astronomy, is fundamentally photons at giga-electron volt energies are rare. Even the brightest sources in the gamma-ray sky produce only a handful of detectable photons per hour in a typical instrument. The diffuse background is built up from millions of photons accumulating over months and years of observation. The signal-to noise in any gamma-ray analysis improves roughly with the square root of observing time. Double the exposure and the signal-to noise improves by about 40%. 16 years of continuous all-sky survey represents an enormous statistical advantage over the first few years of Fermi data that dominated early analyzers. This means that a signal too faint to be statistically significant in the first 5 years of Fermi data could cross the threshold of significance in the full 16-year dataset, even without any change in the analysis method. The signal Totani finds may have been present in the data all along, hidden below the noise floor of earlier analyses, and may have only crossed the threshold because of the time it has taken the dataset to mature. This is a common pattern in astrophysics. The cosmic microwave background polarization was theoretically predicted decades before the instrument. Sensitivity to detect it existed. the first detection of gravitational waves from binary black hole mergers by LIGO in September 2015 was the culmination of decades of instrument improvement that pushed sensitivity below the threshold required to detect events at astrophysical distances. The discovery of the accelerating expansion of the universe in 1998 came from accumulating enough Type Ia supernova observations at high redshift to overcome the statistical noise in the distance measurements. Dark matter signal searches follow the same logic. The expected signal is faint. The background is complex. Only when the dataset reaches sufficient depth does the signal emerge above the noise, if it is there at all. The Fermi telescope may now be reaching that depth. There is a specific observational test that would go a long way toward confirming or refuting the WIMP interpretation of Titani's signal. And it does not require a new telescope. It requires a more detailed spectral analysis of the existing Fermi data. WIMP annihilation does not produce gamma rays at a single fixed energy. Depending on what the WIMPs primarily annihilate into, the gamma ray spectrum takes characteristic shapes. If two WIMPs with masses of 40 gigaelectron volts annihilate predominantly into bottom quark-into-quark pairs, the resulting gamma ray spectrum follows a specific shape, determined by the subsequent decay and fragmentation of those quarks. If they annihilate into tau lepton pairs, the spectrum is harder, shifted toward higher energies. If they annihilate into W boson pairs, the spectrum has a different characteristic form again. Each annihilation channel predicts a specific spectral signature. By fitting the spectral shape of Titani's residual emission to these different theoretical templates, and seeing which one provides the best fit, physicists can potentially determine not just that WIMPs are responsible, but specifically which annihilation channel dominates. This would be an extraordinary piece of information. It would constrain the fundamental couplings of the dark matter particle to standard model particles, which is precisely the information needed to predict what direct detection experiments should find and what particle colliders might produce. This kind of spectral analysis is underway. Multiple groups have announced they are working on follow-up analyses of the Titani result, and the spectral decomposition of the residual will be a major focus of those efforts. The Fermi data are publicly available through NASA's Fermi Science Support Center, which means independent teams around the world can download the same archive and apply their own analysis pipelines. Open data access in this way is one of the cornerstones of modern astrophysics, allowing rapid, independent verification of claimed results. The broader history of the Fermi telescope and its predecessors in the field of high-energy gamma-ray astronomy is relevant context for evaluating the significance of the current moment. Before Fermi, the primary space-based gamma-ray observatory was the Compton Gamma Ray Observatory, or CGRO, launched by NASA in April 1991 aboard the Space Shuttle Atlantis. It was the second of NASA's 4 great observatories, following the Hubble Space Telescope. Among its 4 instruments was EGRET, the Energetic Gamma Ray Experiment Telescope, which produced the first all-sky gamma-ray map at energies above 100 million electron volts. CGRO operated until June 2000, when NASA deorbited it after a gyroscope failure made continued operations technically risky. EGRET's sensitivity was limited compared to Fermi, as its point source catalog contained just a few hundred sources. Compared to Fermi's thousands, its angular resolution was inferior, making source identification more ambiguous. Its exposure was far shorter, but EGRET did identify an excess of diffuse gamma ray emission from the galactic plane that was higher than models predicted. sometimes called the egret excess, which some researchers interpreted as a potential dark matter signal. The Fermi telescope's sharper imaging and broader energy range allowed subsequent analysis to explain the egret excess in terms of a harder cosmic ray spectrum than had been assumed in the earlier models, effectively resolving it as a conventional astrophysical feature rather than a dark matter signal. This history of potential signals being resolved into known physics is important to bear in mind, but it cuts both ways. The resolution of the egret excess did not eliminate dark matter as a search target. It refined our understanding of the astrophysical background against which a genuine dark matter signal must be found. Each false alarm teaches the community something about the complexity of the gamma-ray sky and improves the analysis tools for the next search. Totani's analysis benefits from all of this accumulated knowledge. The source catalogs he used for subtraction are built on decades of accumulated Fermi data and careful analysis. The spectral models for the diffuse galactic emission are far more refined than they were when the galactic center excess first appeared in the literature over a decade ago. The understanding of the extragalactic background is better constrained. The analysis is not being conducted in the dark, it is being conducted with the best available understanding of every known contributor to the gamma-ray sky. One additional aspect of the finding that has drawn particular attention is its apparent consistency with two earlier independent analyses of the Fermi data that found hints of a similar signal. In 2015, a group led by researchers at Johns Hopkins University reported evidence for a diffuse isotropic gamma ray background component that was not well fit by models based on known source populations. Their analysis pointed to a potential contribution from dark matter annihilation, but the statistical significance was modest and the paper was received with measured interest rather than excitement. In 2022, a separate group analyzing the Fermi extragalactic background found evidence for a component with a spectral shape consistent with dark matter annihilation in the 100 million electron volt to several GeV electron volt range. Again, the signal was present but not definitive. Totani's result emerges as the third independent analysis pointing in the same direction. From the same dataset, but with a different methodology and a tighter focus on the high-latitude diffuse emission. Three analyses from different groups using different techniques, finding consistent results, is stronger evidence than any single analysis alone. It is not the same as three independent datasets. The underlying photons are the same in each case, but independent analysis methods applied to the same data and reaching consistent conclusions provide a meaningful check against the possibility that one group's result reflects an analysis artifact unique to their specific procedure. This convergence of independent analyses on a consistent signal is part of why the paper has attracted more serious attention than might otherwise be expected. For a single result claiming a potential dark matter detection, the community has been burned before by signals that did not survive scrutiny, but three analyses spanning a decade, all finding a diffuse excess at similar energies and with similar morphological characteristics, that is harder to dismiss. The theoretical implications extend beyond simply identifying dark matter. If WIMPs are confirmed through the gamma-ray channel, it would have profound implications for the history of the early universe and for our understanding of physics beyond the Standard Model. The Standard Model of particle physics, for all its predictive success, is widely understood to be incomplete. It does not incorporate gravity in quantum mechanical terms. It contains 19 free parameters that must be measured rather than predicted. It does not explain the observed asymmetry between matter and antimatter in the universe, and it has no natural candidate for dark matter. Every extension of the standard model that has been proposed to address these shortcomings either explicitly includes or can accommodate new massive particles in the dark matter mass range. WIMPs, as predicted by supersymmetry, are the most theoretically well-developed of these candidates. But supersymmetry's natural dark matter particle, the neutralino, which is the lowest mass, stable supersymmetric particle in most models, has proven elusive. If the particle responsible for the gamma-ray signal is the it would confirm not just that WIMPs exist, but that supersymmetry is a correct extension of the standard model. The implications for fundamental physics would be transformative. Supersymmetry predicts a doubling of the known particle spectrum, a supersymmetric partner for every known particle. It provides a framework for unifying the three non-gravitational forces at high energies, and it potentially provides a window into the physics of the very early universe, when temperatures were high enough that every supersymmetric particle was freely produced. If, on the other hand, the dark matter particle has properties consistent with the gamma-ray signal but inconsistent with the neutralino or any other supersymmetric candidate, it would represent a form of dark matter entirely outside the standard model in a way that might not connect to supersymmetry at all. This would be evidence for a dark sector, a collection of new particles and forces that interact with the standard model only through gravity, which is among the most exciting and least constrained possibilities in theoretical physics. The dark sector idea has gained considerable traction over the past 2 decades. The absence of WIMPs in direct detection experiments has pushed theorists to consider models where dark matter interacts with ordinary matter more weakly than the weak force through a so-called hidden or dark force mediated by new gauge bosons with very small couplings to standard model particles. In such models, dark matter could annihilate efficiently within its own dark sector, producing dark photons or dark Higgs bosons that then convert into standard model particles at some small rate. The gamma-ray spectrum from such annihilation chains would look different from the simple WIMP2 quarks or WIMP2 leptons channels, often producing distinctive spectral features or different peak energies, whether the spectral shape of Totani's residual is better fit by simple WIMP annihilation or by more complex dark sector models is a question the follow-up analysis will address. The data exists to discriminate between at least some of these possibilities, though the statistical power may not yet be sufficient to definitively distinguish between close variants. What is certain is that the conversation about dark matter's nature has gained new urgency. The publication of Totani's paper in November 2025 has provided the community with a concrete observational target, a specific signal, with a specific morphology at a specific energy against which all models can be tested. This is qualitatively different from the situation a year ago, when the field was characterized more by constraints and upper limits than by positive signals. Positive signals, even uncertain ones, have a different relationship to theory than upper limits do. An upper limit tells you a model cannot predict more than a certain rate. A positive signal, if it holds, tells you a model must predict at least a certain rate. These are complementary constraints, and together they define a range within which the true theory must lie. If the Totani signal is confirmed and the Lux-Zeppelin direct detection limits continue to hold, the combination defines a WIMP that annihilates at a specific rate but scatters off nuclei only weakly, which is exactly the kind of specific constraint that guides theorists toward the correct model. Particle physics has a long tradition of anomalies that turned out to be the leading edge of genuine discoveries. The anomalous precession of Mercury's orbit, unexplained by Newtonian gravity, was a numerical curiosity for decades before Einstein's general theory of relativity provided the explanation. The ultraviolet catastrophe, the failure of classical physics to correctly predict the spectrum of black body radiation, led to Planck's quantum hypothesis and eventually to the whole edifice of quantum mechanics. The anomalous magnetic moment of the electron, measured with exquisite precision and found to deviate from theoretical prediction by a tiny but definitive amount, guided the development of quantum electrodynamics into one of the most precisely tested theories in physics. Anomalies in the data, when they are real and reproducible, tend to point toward new physics. The Fermi residual, taken together with the independent evidence from galaxy rotation curves, gravitational lensing, the cosmic microwave background, and the large-scale structure of the cosmos, represents the convergence of an enormous body of evidence on a single conclusion. There is something real and substantial out there that we have not identified. The question is only what it is, and the gamma-ray sky may now be giving us the first spectral fingerprint of that something. As this story continues to develop, the scientists most directly involved are doing exactly what good scientists do, checking the result, looking for alternative explanations, designing new analyses to test predictions, and resisting the temptation to claim more certainty than the evidence warrants. This is not timidity. It is the discipline that makes confirmed discoveries meaningful. The history of physics is littered with premature announcements of discoveries that did not survive scrutiny. The community has learned, sometimes painfully, to be careful, but careful is not the same as dismissive. The signal in the Fermi data is not being dismissed. It is being taken seriously, studied carefully, and used to motivate new observations and analyses that will, over the next several years, either confirm it as a landmark discovery or resolve it as a sophisticated version of a known astrophysical background effect. Either outcome advances science. If it is confirmed, it is one of the greatest discoveries in the history of physics. If it is explained away, it reveals something new and important about the complexity of the gamma ray sky and sharpens the tools used for future searches. Science wins either way. For the rest of us, for the people who look up at the night sky and wonder what it is made of, who read about these discoveries and feel the pull of the unknown, the current moment in dark matter research is genuinely extraordinary. We are close to 90 years into a mystery that touches the deepest questions about the nature of matter and the structure of the cosmos. The instruments and methods available to address that mystery have never been more powerful. And for the first time, a carefully conducted analysis of the best available data has produced a specific, structured signal that looks the way a dark matter signal should look. The mystery that Zwicky glimpsed in the Coma cluster in 1933, that Rubin confirmed across dozens of galaxies in the 1970s, that simulations and the cosmic microwave background have quantified with increasing precision ever since, may at last be approaching its resolution, not in the sudden flash of a single definitive experiment, but in the patient accumulation of evidence from many directions, converging on a common answer. The invisible thing that holds galaxies together is patient. It has been there since before the first stars formed. It will still be there long after the last star goes dark. But our ability to detect it, to characterize it, to understand what it fundamentally is, grows with every passing year of observation and analysis. The Fermi telescope has been watching the gamma-ray sky since 2008. What it has found, in 15 years of archived data and one physicist's careful analysis, may be the first direct observational fingerprint of the substance that makes up most of the matter in the universe. The case is not yet closed, but the evidence is accumulating, and the universe, patient, ancient, and vast, is slowly giving up its most carefully held, secret. Consider for a moment the sheer improbability of our position. In this story, we are a species that has existed on this planet for roughly 300,000 years. For the vast majority of that time, we understood nothing of the large-scale structure of the cosmos. The night sky was a ceiling of fixed points, the planets wandering lights, the Milky Way a faint smear of brightness whose nature was a mystery. The idea that there could be something invisible, something not made of atoms, pervading the space between and within galaxies, an idea like that was not even conceivable until the mathematics to describe it existed. Zwicky lived at the precise historical moment when the tools for conceiving of dark matter had just come into existence. Einstein's general relativity had been published in 1915, providing the mathematical framework for understanding gravity as the geometry of spacetime. Astronomers had only recently confirmed that the Milky Way was one of many galaxies. The great debate between Harlow Shapley and Heber Curtis about the nature of the spiral nebulae was settled in the early 1920s with observations by Edwin Hubble. The universe had expanded in the human imagination, from a single fixed galaxy to an infinite sea of island universes within a single decade. Zwicky arrived at Caltech and pointed his instruments at this newly expanded cosmos and immediately found something that should not have been possible under any known physics. Rubin did the same thing 40 years later, systematic, patient, rigorous, working against institutional resistance, not all of which was scientific. She built a database of galaxy rotation curves that made dark matter undeniable. The flat rotation curves she measured are not subtle. They are not ambiguous. They are a screaming discrepancy between what physics predicts and what the universe does. And she documented it, galaxy after galaxy, until the evidence was irrefutable. The generations of scientists who have followed, building the underground detectors and the space telescopes and the particle accelerators and the supercomputer simulations, have each added a piece to a puzzle that grows more precisely defined with every passing year. The shape of the puzzle is now clear. The outlines of the missing piece are sharply drawn. Its gravitational effect on everything around it is measured with extraordinary precision. Its particle nature remains the mystery. The Fermi signal may be the first time the puzzle piece has made a sound. That is where the science stands. And it stands at the threshold of a discovery that, if confirmed, will take its place alongside the greatest moments in the history of human understanding. The identification of dark matter's particle nature will not just fill a gap in a table of known particles. It will complete a description of the universe that has been incomplete for 90 years. It will confirm or refute theoretical frameworks that have guided physics for decades. It will illuminate the first moments of cosmic history in ways that no other discovery could. The search continues. The instruments are running. The data are being collected and analyzed. Somewhere in the high-latitude gamma-ray sky, in the diffuse halo-shaped glow measured by a satellite orbiting Earth, in the pattern of photons that arrived from the dark expanse of the Milky Way's invisible outer structure, the answer may already exist. It is waiting, as dark matter has always waited, patient, massive, invisible, and fundamental. What Totani found is, at its core, the product of a simple and powerful idea that if dark matter particles annihilate each other, the universe must be producing a faint but detectable glow from the regions where those particles are most concentrated. That idea is not new. It has motivated searches for decades. What is new is the quality of the data. 16 years of accumulated photon statistics from the most sensitive gamma-ray observatory ever built, and the rigor of the analysis that stripped away every known source of contamination to reveal what was left. What was left is shaped like a dark matter halo, What was left peaks at the energy a dark matter particle of 40 gigaelectron-volts would produce. What was left is not explained by any known astrophysical source, population. It is a residual, in the mathematical sense, the remainder after everything known has been subtracted, and the shape of that remainder looks exactly like what theorists predicted decades ago, before the first photon of the Fermi era was ever collected. Predictions made before the data are more credible than explanations constructed after. The halo shape and the WIMP annihilation spectrum were both predicted on theoretical grounds, long before the Fermi telescope was designed. The observation either matches those predictions or it does not. According to Totoni's analysis, it does in both spatial morphology and in energy spectrum. Simultaneously and independently, that double correspondence between prediction and observation across two completely separate and independently measured properties of the signal is the foundation on which the scientific community's interest rests. Single correspondences can be coincidental. Double correspondences are harder to dismiss. Triple correspondences add in the fact that the implied WIMP mass is consistent with the thermal relic abundance calculation that independently predicts the correct dark matter density border on the compelling. The path ahead is clear, even if the destination is uncertain. More data from the Fermi archive will be brought to bear. New analysis techniques will be applied. The Cherenkov telescope array will eventually begin operations and bring superior sensitivity at high energies. The Rubin Observatory will expand the catalogue of dark matter targets. The Luxor Zeppelin detector will continue probing the direct detection parameter space. Each new measurement will either strengthen the signal's case or constrain it further. And somewhere in all of that observational and experimental work, the 90-year question that Zwicky first formulated will find its answer. What is the dark matter? What is the invisible mass that holds galaxies together, that scaffolded the large-scale structure of the observable universe that constitutes most of everything? The universe has been keeping this answer for a very long time. The instruments we have built and the scientists running them are finally close enough to hear it. If this is the kind of discovery you want to be around to witness, stay close to the science. It moves fast when it moves, and right now, it is moving.